Form 7 Physics, Unit 4, third term content, Electric Field and Coulombs Law. In this video, we are going to focus on the spec points 92, that is to understand what is an electric field, and 93, understand the electric field strength and define the electric field strength by the equation E equal F over Q, and spec point 94, able to use the equation F equal Q1 Q2 4 5 epsilon 0 R squared for the force between two charges. That's what we call Coulombs law. Let's move to electric field, or what is force field. It is a region of space in which a charged particle experiences a force. If you observe a particle experience a force, if it is charged, so we can call the area or space where the particle exists is an electric field. That is the basic idea. And here it shows two particles, that is, one is positively charged, one is negatively charged. So what are these lines? So lines have been drawn. So that shows there's a field. To show the field, we represent the field by drawing field lines. So what is these electric field lines? So let's observe this. So here positive charge, here negative charge. We can see that field lines start from positive and ends in negative. So this gives an idea what is an electric field line. So it is the pathway of a positive test charge in an electric field. We have learned in our O-level classes that how the charges behave. Like charges repel, unlike charges attract. It means positive and negative attract, negative repel, positive repel. Now if you think that if you keep a positive charge here near the positive charge, what you expect? Repulsion. So that's it, repulsion. So it repel and move away from the positive charge. So we can say that electric field line start from the positive charge. It's moving away. And if you keep a positive charge close to the negative charge, what will happen? It will attract. So the field line towards the negative charge. That is the nature or behavior or feature of the electrical field line. It starts from positive and ends in negative. And if we think the strength of the field, or how strong the field is, that also we can have an idea from the field lines exist. Now if you consider area here and another area there, so what is the difference of these two enclosed areas? Here number of field lines enclosed is 2, here about 3, 3 to 4, right? So we can say that by looking at the number of field lines enclosed, we can say that here this area is a stronger field, this area is weaker, as number of field lines enclosed is less. Let's move to discuss about what is radial electric field. Radial. Now negative charge, you can observe the drawn field lines around it, and here is a positive charge, you can observe the drawn field lines around it. What is the feature? The basic feature is there. Here negative charge, the field lines comes towards. Here positive charge, field lines moves away from it. And there's another difference if you observe little closely. Now I have selected an area here, little bit far from the charge, another area but is close to the charge. Then what can you say about the strength of the electric field? The number of field lines here enclosed by the area is more than this. So we say that the field strength here is greater than this. So what is the difference of these places? This place little bit away or away from the charge, here very close. So then we can tell about the radial electric field, one idea, that is, in the radial electric field, the field strength is greater close to the charge and weaker away from the charge. That is very important to keep in mind. And other thing, that the field line direction, if it is negative, it is towards, and if it is positive, it is away. That is the basic thing what we have learned about the field lines in the previous slide. Then let's move to understand what is the nature of uniform electric field. Uniform. So when you get the word uniform, that the consistent nature is there in the word uniform. Uniformity, uniform. So observe this: two charge metal plates, and this charge positive, this charge negative. So obviously the field line start from positive and ends in negative, so that feature is there. Another feature is existing here. Not like radial electric field, the field line spacing is similar. So we call that is equispaced, equally spaced. That's the meaning of equispaced. And the field lines are parallel. But in the radial field, you have not observed that field lines are parallel. And when it is close to the charge, it is closer. And when it is moving away from the charge, it is little bit moving apart each other. But here, everywhere, the field lines with the same spacing. Now, shall we observe the two areas like earlier? Now here, this area, number of field lines enclosed is same with this area. So we can say that the field strength in this place and this place is same. So I have select only two places. It is like that in the area between the two charge metal plates. So that you have to keep in mind the difference between the radial electric field and the uniform electric field. Now let's think of force act on a charge. So basic idea of electric field, in the beginning we have stressed that what is an electric field is area or space where a force act on a charge. So that basic idea we are taking it to give an idea of the force that act on the charge. Now charge object in an electric field experience a force. That is what we call electrostatic force. If the force is F and the strength of the field is E and the charge is Q, the relationship between force, field strength and charge is given by this equation. F equal E into Q. F, electrostatic force given in Newton. E, electric field strength, unit is Newton per Coulomb, and the charge of the object, here it is Q, unit Coulomb. Then let's have an idea about the electric field strength also. Now what is electric field strength? Now we have learned that from this relationship, but the relationship force, electric field strength, charge relationship, force is equal field strength into charge, F equal EQ. Now what is represent E here is the field strength. If we object the letter E in this relationship, what we can get? Now F equal EQ. So if we object E like this, so the Q moves down, Q moves down. So force over Q now. Electric field strength is force over Q. If what is F, force charge into field strength, F equal EQ. So then what is field strength? E, capital E is the letter that we are using to represent the electric field strength. It's given by electric force F on a charge in Newton divided by the charge in Coulomb. So we can say what is E is force per unit charge. Force per unit charge. Force is Newton, charge is Coulomb, then force per unit charge, the unit will be Newton per Coulomb. Newton per Coulomb. So when we describe the field strength, we have to say that force act on unit charge, that is correct, but we have to stress that is positive charge, because electric field strength has a direction. The field strength direction, as we have observed earlier about the field lines, that is away from the positive and towards the negative. So it is very, very essential to mention when you say about the electric field strength, that is the force F act on a unit positive charge. Unit positive charge. So let's have an idea a little bit more further about the field, the electric field. So field line start on positive charge that we have learned, and field line stops in negative charge, and more charge, more field lines. Now when you compare the Q, here Q to Q, greater charge. So when the charge is greater, field lines is greater. Why field line is number of field lines is greater? Field line represent the field or the strength of the field, and here the strength is more than this. That is the idea. And also another point you have to keep in mind, field lines never cross, and also the distance between field lines is more. If it is more, it is weaker area, and it's close, it's strong area. So if we want to find the direction of electric field strength in a field, if the field lines are drawn, so if we draw a tangent, to the field line, that at that point the tangent shows the direction of the field line in the field. So here positive, it is away. Then if you draw a tangent here, the tangent direction is away from the positive charge. That is the electric field direction, or the field strength is a vector quantity. So definitely it must have a direction and a value, magnitude. Example 1. A proton of charge plus 1.6 into 10 to the power minus 19 Coulomb is moving in an electric field strength 500 Newton per Coulomb. This is charge, this is the field strength. Here Q, here E. So we have to have an idea. Okay, what the first question is, what is the electric force? So obvious, F equal EQ. Now you have a little bit familiar with the relationship by now. So F equal EQ. So what here we have to write is F we need to find out by using E and Q. And part 2, how does this force compare with the weight of a proton? Okay, let's see what are the answers. So first part, as we discussed, force is equal EQ. The electric force is calculated. E substitute, Q substitute. Here the Q, don't expect to give the Q in the exam questions, because the charge of electron is given in the back of the paper in the formula sheet. So here, but it is given. So if it is not given and say it is proton, you must understand the charge is this. It's similar with the electron charge, and we can calculate, multiply field strength and the charge. So we have the answer 8 into 10 to the power minus 17 Newton is the electric force. The second part, they say to compare the force, this electrostatic force, with the weight of the proton. So before comparing, then we must find the weight of the proton. How to find the weight of the proton? Weight is equal mass into gravitational field strength. So weight can be calculated by using mg, W equal mg. So m is the proton mass and g is the gravitational field strength. So we have the value 1.7 into 10 to the power minus 26. So when you compare these two, you can see that this is bigger and this is small. It is 10 to the power minus 17, 10 to the power minus 26. When the minus power is more, it is small. Then now here are comparison. So we can just say, can we just say that weight is small and force is big? No. So if it is possible every time in a comparison, we must say how much big. Then in order to obtain an idea for that, I have worked out here the bigger value I have put on the numerator and small value as the denominator, so get the ratio. So I have got it 4.7 into 10 to the power 9 times bigger. The electrostatic force is bigger, 4.7 into 10 to the power 9 times. So it is nearly 5 billion times than the gravitational force. So this is also a good idea to have when you are dealing with sums. We can always ignore gravitational forces when dealing with electric force on charged elementary particles. Example 2. What is the acceleration of a singly charged nitrogen molecule of mass 4 into 10 to the power minus 26 in an electric field of strength 360 Newton per Coulomb? So singly charged means the charge of electron it's having a charge of electron, that is 1.6 into the power minus 19. The force act on the charge is given by F equal EQ. Then the force we can calculate as we have given E 360 and charge 1.6 into 10 to the power 19, and we have the force act on it, that is 5.76 into 10 to the power 17 Newton. But the question is about the acceleration. So what is this? This is the force. What force then? To have an acceleration, resultant force. Correct. So this will be the resultant force to have an acceleration. So we have to use the F equal ma relationship from the Newton's second law, force mass into acceleration. So force is given by the electrostatic force, we substitute there, and mass given, and we can calculate the acceleration, that is 1.4 into 10 to the power 9 meters per second square. Let's move to have an idea or have an understanding about the Coulombs law. What the Coulombs law says. Now it is describing the electrostatic force exists between the two charged objects. So the two charged objects I have select, one has Q1 and one has Q2. So Q1, Q2. So this is the electrostatic force. So it is proportional to the product of the two charges. Directly proportional to the product of the two charges. And what is this R? Is the separation between the charges. Now keep in mind the separation not from the surface, it's from the center to the center. That is very important. Center to the center, separation is R. So that is inversely proportional. Separation squared is inversely proportional. So that's what we give or we express as the Coulombs law. Electrostatic force between two charges Q1, Q2 is directly proportional to the product is the Q1 into Q2 of the charges, and inversely proportional to the square of the separation. Separation is not the radius, don't misunderstand, is R. R is used for the separation, that is from center to the center. So this is the equation. K is the constant, proportionality constant, which is called Coulombs law constant, and that is equal to 1 over 4/5 epsilon 0. The value of K, it will be there in the formula sheet, is 8.99 into 10 to the power 9 Newton meter square per Coulomb square. Now observe this what we have come across earlier slide, and observe these two charges. When this big, the arrows are getting bigger, that is arrows represent force, arrows represent bigger. When they further apart, then they have become smaller, but when this small, this also small. So when they come closer, the force increases. So you can observe and predict this behavior from this equation. When the charge big, the force big. When the separation small means they are coming closer. When they come closer, as it is inverse relationship, when R is small, squared and also squared, the effect is more than the force will be When this is small, force will be increased. When this is higher, that is separation is greater, then the force will decrease. That is the idea of this animation. You can get a better idea by looking it and have a look on this, with a look of on this. Measure the force between two charges. This is, so here two charges are there. So this is on the top pan balance and this is hang. Both here use insulating support, here insulating thread and wound around insulating rod, and by decreasing this top charge we can we can increase the distance or the separation between this. When this lower, the separation small, then what we expect as positive and negative, the attraction to increase. When this attraction increase, this charge will lift up and we can expect the decrease in the reading. So decreasing in the reading represent the force decreases, and as this is very small values, the force is small value, so we need the more sensitive top pan balance, and we can't touch these charges as they get discharged by touching. So we have to use another method, but we do to measure the separation, not touching. Now if we keep a ruler here also we can measure, but we can't select the center and all. So we have a light source here and we can place a screen here and we can project the shadow into this onto the screen, and from the shadow center to center we can measure the separation, and varying the separation we can measure the force change according to it. And now how can we take the shadow separation as the actual separation here, but it's not directly, we can't take it as this because this will be getting vary as the light source closer, then it will be more big, and it's depend on the presence of the light source here and the distance to the screen. So if we are doing this experiment, we have to keep the position of the source and position of the screen constant. If we keep them constant, so we can take the actual and the projected separations are proportional, so we can test about the behavior or the variation from this. So you can observe that. So I have mentioned this in for you to refer, and so you can, I have jot down here the points what I have discussed, and this here I have mentioned how this being charged here by flicking or the rubbing from a cloth, and here by connecting it to a positive terminal. So this to get charged, and we have to maintain the charges, otherwise throughout the experiment, otherwise the variation can occur. So example 3. Two identical table tennis balls M and N are attracted to non-conducting threads and suspended from point P. The balls are each given the same positive charge, and they hang as shown in the diagram. M and N hang from the point and from the thread. This also from the thread. So here non-conducting threads from a point and ball, each ball is given the same positive charge. So whether it is positive or positive or negative, it can be, because here what you can observe is the repulsion. So the charge on M should be equal type of charge with N, otherwise the repulsion won't occur. So that is the basic idea that we have gained. So part A show that the tension is the force acting through the thread is about 3 into 10 to the power minus 2. So here we have to consider the vertical equilibrium. Now tension acting on this, so it is forming an angle with the vertical, that is 35 degrees here from with the vertical. So tension resolved vertically, that T cos 35 should be balanced with the weight mg. So we can substitute the values T cos 35 equal mg, then we can object T. So m is given in grams, we have to convert it to kilograms. So G is 9.81, substitute, and cos 35 we can have the value, and we can find the value of T, that is 3.2 into 10 to the power minus 2 here, 3.23. we have to concern and look at the third significant figure to round up to second significant figure, as the question request 1 SF. So 1 SF they request. Keep in mind as the rule, if they request 1 SF, we have to provide at least 2. To round up for 2, we have to look into the third significant figure. Part 2, show that the electrostatic force between the ball is about 2 into 10 to the power minus 2 Newton. That also show that question. So here what we are going to equate, earlier we equate the tension of the thread with the weight. So we resolve the tension vertically. Now what we are going to do, resolve the tension horizontally and equate with the electrostatic force. So electrostatic force away from the M, that is equal with the tension horizontal component, that is T sine 35. Now here the angle that it formed with the tension thread is 35, so we resolve it horizontally, then we get T sine 35, that is equal to F, the electrostatic force. So we have the T calculated earlier, so multiply with the sine 35, we get 0.018 Newton. That is round off for two significant figure, as the requesting is 1.8 into 10 to the power minus 2 Newton. Part 3, calculate the charge on each ball. So we have calculated the electrostatic force, use the Coulombs Law relationship, F equal K Q squared over 4 pi epsilon 0 R squared. So here we can use the constant K or this 4 pi epsilon 0 relationship. So we have the value of K. In order to find out Q, we object Q in the relationship, and F we have got it in the earlier question. So R we have, and divide by the K. So we can obtain the Q by calculating and square root the Q squared. We get 3.07 into 10 to the power minus 7 Coulomb. Part B, state and explain what would have happened if the charge given to ball M was greater than the charge given to ball N. Now, as you have observed earlier simulation, that when the one charge increase, what we have noticed, one charge increase, the force increase, electrostatic force increase, but it's same manner it acting on both. So we can understand that as the Newton third law pair, the force act on N is equal to the force act on M by the N. So the force will increase on acting on both, and the angle will increase. That is what can happen on the ball suspended at equal angles. So this angle will be more than 35, but this also 35, this also 35. Now if the force increase, this will go like this, like say more than 35 will be this, and that this angle also will be the similar to this with the vertical. Now let's summarize what we have learned. What we have learned, what is an electric field, and use the relationship F equal EQ, and we use the same relationship to define the electric field strength as E equal F over Q, and interpret radial and uniform fields, and use the expression F equal K Q Q1 Q2, that is QQ, or Q, we can sometimes use Q squared if it is similar, over R squared, that is Coulombs law. Thank you.